That's wild. All right. Bye, I love you.
Do you guys know how to work this touch panel?
Yeah.
And to like move the camera?
Yeah.
Okay, so you're in good hands then. So the quality of the audio has been really bad. I don't know if they've mentioned that at all. On the far end, they haven't been able to hear us in like all these calls. So there's been 2 microphones. There's one in here. I've disabled those microphones, and it's coming only the microphones are this thing.
Only from there.
Sounds much better. So I don't know if anyone's complained, but
Cool, thank you.
yes, I'm gonna check one more thing. So also when sending content, it's been not doing it. So do you guys send content ever?
Don't think so.
Yeah, no.
Okay, anyways, get out of here. Goes down there. Thanks.
Yeah, have a good one.
Other kinds.
You should mute us.
Hello, can you hear me? Is it,
Yep, we can hear you.
is it correct that this is your last class?
This is our last class, yeah. Are you holding a class on Friday?
Yes. So do you need the video?
That would be good, yeah.
Okay. I will talk to him. So you heard me, yeah? He still needs a Friday video. And on Monday there's no video. So it's over.
I think they record them all automatically.
Okay.
But I'll let her
So, thanks for coming. End of the semester.
Well, so they don't have that 8 a.m. class, except that.
The time is good, right?
Is there a first day class? Pardon? Yep.
I cannot find you.
It may then, right?
But it's not bad at all. So the test results are excellent. Congratulations. I want to know how it works. Otherwise, I will show you the complete solutions because the final will involve problems like this. So what you have to expect on the final is a mix of test 1 and test 2 problems. Again, the setup is exactly the same. So I show you the solutions for complete clarity. Let me quickly double check that I did not make any mistake. One second. Yeah, please. Yes. Thanks.
We have a question on number 1.
Number 1, yeah?
Should the sum start from 0 or 1?
You can write it either way, so it doesn't matter. You can write it in both versions.
Okay.
It's good. It just modifies slightly the writing of the BN. So in other
Got
words, when you introduce here an M that runs from 0 to infinity, then you have to adjust the setup in order to get it correct. But this is one correct version, okay?
Got it.
So I did not observe any real problem with respect to 1, except in some cases it was about accuracy. So we had one longer problem which was pretty similar, and then it is about the correct eigenvalues and exactly about whether this runs from 1 or 0, whatever. So in some cases I saw no squared eigenvalues. I saw eigenvalues like n pi squared, things like that. So little things. But overall, everybody had a very good idea of how to do this. Regarding number 2, I did not observe any problem except when it came to the condition on lambda. There are 2 conditions, as we discussed in class and as we also discussed regarding the last homework. One condition is due to the convergence of the geometric series, and one condition is the overall condition for the convergence, actually the uniform convergence, which reflects, let's say, the domain considered. And this condition needs to be sharper or as sharp as the convergence condition for the geometric series. So in this case, it turned out that an absolute value of lambda smaller than 1 makes the job. And the condition that lambda has to be smaller than 3 is actually too weak in this case. There's an excellent chance that you will see a problem like number 3 on the final. I can only repeat again and again my request to be very, very careful with the setup of the Euler-Lagrange equations. It looks so simple, but any little mistake at this point has kind of bad consequences. Usually the problem becomes much harder. So it is just good to write it, to double check, to triple check, whatever, but to make sure that the equation is correct. Then, after getting the solution, what I always do is to check whether my solution satisfies the initial conditions. Otherwise, excellent job. I don't think that anybody has to worry about something. Yeah? Very good. So I will send you the PDFs this afternoon. So what I will do is to finish the final preparation. So when I showed you this before, I showed you the structure of doing this, and I told you that I started the finance preparation with methods of applied 1. Then, to make sure that we have sufficient time, I talked about the second part to prepare the test, and now we switch back to the second part of 1B, and the plan is to finish this today, and then you are fully prepared for the final. There will be no class on Monday because it does not make sense. What I will do on probably I will begin with that today, and on Friday I will talk about the Laplace equation, just to give you an impression of how solutions to such problems look like. This will be not involved in the final. It is not part of any qualifying exam. It is just kind of background to know about ways to deal with these cases. Also, I was asked to ask you to respond to the teaching evaluations. Every instructor is doing his very best for you every day, and you know that, bless you, this matters to the department. It is really important. So please take the 5 minutes to respond. I would highly appreciate this. Okay? So we talked about methods for second order equations. And this is for the bounded domain case. And what we did last time was to consider the 1D case, so homogeneous PDE and homogeneous boundary conditions. We did this. So I showed you for the wave equation and for the diffusion equation the Green's function representations. Then what we should also do is to consider the inhomogeneous PDE and inhomogeneous boundary conditions. And this is something that you can also really expect on the final. So when you think about the final as a reasonable mix of test 1 and test 2 problems, then you have a very good idea. And actually, when you know all of that, what I present here in my summaries, then you are perfectly prepared. So the basic idea of this class is actually to learn about strategies, to learn about different ways to address problems, and also to get a feeling about what makes sense under certain conditions. And there are options. And I will talk about a third option in a minute, the Green's function approach. So what you will see is a concrete problem, and you have to decide then what to do. And here there is the option to work with shifting the boundary conditions. This is actually a very nice thing. It is very simple, very straightforward. And if I would have, let's say the choice to do this or that, I would shift the data, because then I can shift the problem in a very simple, clean setup to another sort of problem, and I know the solution for this. So this is something that is really good to do. What we also considered was to adjust, to work with adjustments of solutions to homogeneous problems. So we worked here with UN, which is just another way to do this. When we discussed homework and also test 1, in some cases there were questions about arguments. So of what depends actually on T, and what is independent of T, and things like this. And there were also questions about providing the complete formal solution. So when you have a problem like this with any non-specified big F, you just go with a big F, of course, but what you need to do is to explain how to get the Fn. That needs an expression to explain how to get the Fn. Otherwise, the problem is not completely solved. And if the F is specified like X or T, then you are supposed to solve these integrals. You can use whatever you want except iPhone's internet, but your tables, it's not the point here. The point is to demonstrate an understanding of methodology. So this is one possibility, and then in particular with respect to the diffusion equation, we talked about the Green's function approach, and obviously we can do here the same. So I show this for completeness in order to demonstrate that there is a Green's function representation for everything, which is good. Otherwise, when it comes to the test, I'm not sure how many of you are really interested to go with it, because as you can see, it needs quite some care, and it is related to UU conditions. So if we have, let's say, different values, eigenfunctions, the Green's function will change, and this needs to be reflected. So usually it is much better way to have, let's say, a thorough understanding of the main approaches and ways to deal with modifications. So like shifting the data, that is much more safe compared to doing things like this. But otherwise, it is kind of good to know that there's a Green's function everywhere. So this was with respect to the wave equation. And then for the diffusion equation, we have something comparable. So this follows the same setup, and obviously this is only one approach, and we derived this formula by looking at U is the sum over UN times the eigenfunctions. Then we got an equation for UN, solved the equation, including the force, and then when you plug in the expressions for UN in your eigenfunction expansion, then you get a writing like this if you identify the Green's function. But otherwise, the setup of these problems is absolutely comparable. So, actually, we are done. This is what you should know for the final. And again, the setup is very similar to test 1 and test 2. What I will do is to begin with showing you, let's say, main features of how to deal with Laplace and Poisson equations. This is like some sort of background. It is good to know it, but I will never ask you to show any work on this. I show you here a diffusion equation. And I could also use a wave equation. The point is that we look at Poisson and Laplace equations when we talk about stationary solutions to wave and diffusion problems. Is this important? Yes, this is extremely important. As you can imagine, whenever you have any natural process, there is some sort of artificial state, initial state, and then all what happens is to go from this kind of artificial and arbitrary initial state to something that tells you about the mechanism of the system, so the stationary solution. This is usually our goal to understand what this is finally about. So, and again, we have here the same equation for stationary wave and diffusion problems. So when we have delta U equals h, h being something, then we talk about the Poisson equation, which is also sometimes called the inhomogeneous Laplace equation. And if the h is 0, then we talk about delta U is 0, which is the Laplace equation. Solutions are called harmonic functions. Is this trivial? It is far from being trivial. You will see it next time. Is this important? Yes, this is extremely important. For example, when it comes to fluid flow problems, usually we have no other option in many cases than to numerically solve fluid flow equations. And one of the most ingredient things of such codes is to solve the Poisson equation for pressure. And this is something that is very important, and very often a huge amount of computational time goes only into this pressure calculation, like 90% sometimes. So it is something that is very important also to flow in porous media problems and so on. So as you can imagine, we can combine this with a variety of different boundary conditions. So if the equation is delta u equals 0, then all the information that enters the problem is via the boundary conditions. So boundary conditions are not anything that is, let's say, kind of a little modification, but it decides about what we get out here. And as you can imagine, we talk about the same sort of boundary conditions that we considered before, so U conditions, U prime conditions, and mixed conditions. And obviously, in every case, we get different solutions. So it does not make sense to go into any technical details today. What I will show you next time is a basic approach to deal with these problems, and I will introduce Poisson's formula, which is kind of nice. So otherwise, the big news is we are done with, almost done with the semester, and on Friday we will talk about this addition. My request is again to respond to the teaching evaluations. So have a good time, and good luck.
Even if you were planning on responding negatively.
No, I don't want to. Please be positive. Think positive.
If you say a stationary problem, then you're just saying UT is equal to 0, right? Like I've gone to the point.
Thank you.